Tonight, we are actually celebrating, this whole year actually, we're celebrating the 10th anniversary of the Our Universe Revealed lecture series. This series started in 2015 at the University of Notre Dame, and then it moved to the library just 4 years ago to make the talks more accessible to the public. And so currently this is a partnership between the St. Joseph County Public Library, Indiana University South Bend, and the University of Notre Dame. At the library, we have hosted 30 talks since 2022, and these talks are video recorded and have had over 20,000 views to date. So people are watching, and we're very grateful for that. I want to give a shout out to Adam Raschke and Nick Myers, who are doing the video recording tonight. This series would not be possible without the help of some people who are kind of behind the scenes a little bit. A shout out to Logan Lee, who is the programming coordinator for the library. He makes sure the tech is all ready, and we're really grateful for his support. Mel Lutz is the community service executive manager for the library, and she also helps with the programming. And then Tammy Freeling is the director of communications and external engagement at Notre Dame, and she has helped. She and I have partnered together to reach out to potential speakers and put together the series. And then finally, Jonathan Crass. The series wouldn't exist at all without Jonathan Crass. So he modeled the Our Universe Revealed lecture series, or the physics. It started as Physics for Everyone, after a free public science series of talks at Cambridge University. And then when he came to the States, he brought that idea with him and started it here. This series features research and creative work that's being done in all fields of science. So as I mentioned, it started off with physics and astronomy. 4 years ago, we started doing all fields of science and really celebrating the creativity and the arts and connections between the fields. And so we've had talks on all different kinds of things, from solar eclipses to the opioid crisis to emerging pathogens to AI technology and what it means for society. And then for the arts, of course, we've had chemistry in the arts, how you can look at art paintings and understand chemistry concepts, thinking about music from a mathematical perspective. We've been dancing to generate theorems in mathematics, and then also looking at origami and thinking about the mathematics of origami. So really a very diverse set of topics. And then this series wouldn't be possible without all of you, and I thank you all for being here tonight. I know it's kind of snowing, it's been kind of a rough couple of days, but you took time out of your schedule to be here. And over time, we've had we're just grateful for a lot of different people who have been here to participate in this series. And so you've all been really curious and asked the best questions, and so it's been a real pleasure. So without further ado, tonight, Dr. Jonathan Crass is an instrument scientist at The Ohio State University. He's been there since 2022. He earned a master's degree in physics and astronomy from the University of Manchester in the UK. He received his PhD in astronomy from the University of Cambridge, and then served as a postdoctoral research associate and then a research assistant professor at the University of Notre Dame from 2014 to 2022. It was at the University of Notre Dame where he worked on the development of the iLocater that he's going to be talking about tonight. At The Ohio State University, he has continued developing astronomical instruments, and particularly specializing in those with diffraction-limited performance for the study of exoplanets. We will hear more about this work tonight. From the get-go, Jonathan has been a really strong advocate for public science outreach. He's given public talks all over the world in the field of astronomy. And then, of course, starting the Our Universe Revealed lecture series in South Bend, making science research more easily accessible to all of us. And so we're really grateful for that. So without further ado, I'm going to turn it over to you.
Thank you, Deb. Before we go into exoplanets, I just want to go back to that picture of me right there. My first talk in the Our Universe Revealed series was a demonstration of the pressures and temperatures in the solar system for kids. So we had hydrogen balloons, liquid nitrogen, dry ice, all the kind of fun stuff. Notre Dame now has its Christmas lecture series where you have all of that stuff. So I like to think we were the precursor to some of those Christmas lecture series they now see. In addition to all of that, I actually do research. And tonight, I'm here to talk to you about that science and that research. But I'm also here to tell you a story. And that story starts with an initial spark of an idea from a professor at Notre Dame, before I was even here. And through the efforts of a broad team of people, it grows into a research project and a new instrument for this telescope you can see here in the background, the Large Binocular Telescope. That project is iLocater, that I'm going to talk about. And within its story and its history, there are various characters, all playing their part. There are successes. There are failures and challenges along the way. And frankly, at this point, 10 years after I started on the project, now actually 11, there are parts of it I've probably forgotten, or I look back with rose-tinted glasses with a very different perspective today than I had at the time. But everyone's efforts along the way have been an important part of this story to get us to the point where the iLocater project is almost finished for the LBT, and I'll tell you a little bit more about that at the end. So if you look up at the night sky, like you can see in this image here, it can evoke profound questions about humanity and our existence. Civilizations for millennia have wondered what the spots of light are in the sky. Wondered, how did they get here? How did we get here? What does the future hold? And that's an integral part of human nature, wondering about those fundamental ideas. Now, as an astronomer, one of the questions I get asked most often at these public lectures is a very simple question. Are we alone? And while the question itself is simple, the answer itself is a little more complex. 30 years ago, astronomers had no real idea about the answer to that question. Now, I know for some of you who've come along to the series regularly, you've already had talks about exoplanets. I'm going to talk about the now 6,000 exoplanets we know of that are confirmed. These are planets orbiting stars other than our sun. Extrasolar planets, or exoplanets as we call them for short. How we detect them tells us different things about them and tells us about the different types of planets. Is our solar system special? Is the fact that we only know about our own solar system and how it looks a real effect of the universe or a limitation of our technology? So if we think a little bit about the techniques that astronomers can use to study the night sky, and particularly these exoplanets. How many of you saw the total eclipse? Okay, so we have astronomical objects that pass in front of one another, blocking out light. And we can have planets pass in front of stars. If you've seen the transit of Venus, the transit of Mercury, you might have seen this as well. So if you measure the brightness of a star and a planet happens to pass in front of it, the brightness of that star is going to dip a little bit. And the planet will pass in front, come out the other side, and the star will increase in brightness again. This is the transit technique we call. Just like the transit of Venus and Mercury, we see this in exoplanet systems as well. How many of you have heard of the Doppler effect? Okay, how many of you have heard the Doppler effect? Every time you hear a police car go down the street and change its siren pitch, you hear this in sound. But it also applies to light. And if we have a planet orbiting around a star, as you can see in this video clip, this is very much not to scale. Planets are not bigger than stars. What we see is the light from this star changing in color, just like we hear the sound change, as the planet orbits. These two orbit around each other. And we can measure this Doppler shift, these changing colors of light, to detect these planets around them. This is what iLocater uses, and we're going to talk more about that in a little bit. Another technique we can use is actually direct imaging very young planets. And Professor Jeff Chilcote up at Notre Dame actually works on this on the GPI instrument, where we can take images of newly formed stars and planets, like you can see down here, and over the series of many years, this one runs for about 10 years now, we can start to see planets orbiting around their stars. We also have stars that pass in front of each other. Our galaxy and the stars in it are moving. And if they happen to line up, and one of those stars has a planet, the nearby one, again, we measure the brightness of those stars, and we see a change in that blip and brightness. Now, we haven't discovered that many microlensing planets yet, but starting next year, that's going to be a big thing that's going to come more into our exoplanet studies, and we'll talk about that at the end. So one of these different techniques told us they actually are sensitive to different types of planets. And the Kepler mission, which was launched back in 2009, was one of these transit missions to study these exoplanetary systems. So if we take this cartoon, this is an image of our solar system. The sun would be in the center, and we have Mercury, Venus, Earth, and Mars. If I play this forward in time, this represents how the planets orbit around. So if we look at Earth, going once around this circle is the equivalent to one Earth year. So it gives you a sense of time and scale. So the Kepler mission studied a small patch of sky looking at all different types of planets. And if we zoom out fully, let's see if it's going to play. There we go. Each of these circles at the center is another star with different planets going around. The size of the circle represents the size of the planet. So these ones are much bigger than those planets in our inner solar system, and the colors here tell us about their temperature. Blue is similar to our Earth planets, but as we go to red, we get up to temperatures of lava. So we have a lot of planets close into their star. Jupiter-sized planets close into their star. Nothing like our own solar system. So we got the results from Kepler, and astronomers scratched their head and went, well, is it a case of that it's our own solar system that's special? The answer is no. It's a limitation of the technology of being able to detect planets like our solar system. So then we went, let's go build another instrument that can do this better. We have new technology, and that's how we do things in astronomy. We take the new technologies, make more precise measurements to help us explore more of the universe. So that was Kepler. What about moving on to the radial velocity technique? What do you think you're looking at in this image? Aside from it being a pretty rainbow color. Yes? It's a spectrograph. What is it looking at? So if you take a spectrograph and you point it at the sun, this is what you would see. This is actually a spectrum of our own star, the sun. And what you see are all of those lines on its surface. And these are the lines that we try to measure when we're trying to use the Doppler technique to discover these exoplanetary systems. So if we come back to that cartoon again, you can see these lines wobbling backwards and forwards in color to detect those planetary signals. We're trying to measure those individual lines as they move backwards and forwards. In this cartoon here, the star itself, it's nice and calm. It's nice and quiet. If any of you had a chance to see the Northern Lights in the last couple of years, certainly heard about them. Does that suggest that stars are nice and quiet and well-behaved like they are in this picture? No, they're not. And if we think about the planets we can discover with the radial velocity technique, think of this on the left-hand side of this plot as being big planets up here, smaller planets down here. And we look at when planets were discovered along the bottom. So the first planet discovered orbiting around a star like our sun was in 1995, which was 51 Pegasi b, and this was awarded the Nobel Prize in 2019. And if we look at the planets we've discovered in the year, you can see we started with big planets, massive Jupiter-like planets, and we can get to smaller and smaller planets as our technology gets better. In 2003, a new spectrograph came online called HARPS in the southern hemisphere, and we got down to more and more mass planets, smaller planets. If we play this forward, scientists like to predict what's going to happen in the future, and we take a line and we extend it. This blue line represents how big the signature for Earth orbiting around the Sun is. It is 9 centimeters per second, less than 4 inches per second, that the Earth causes the Sun to wobble. And if we play this forward in time, you would say the technology is getting better, we're building better and better instruments, we should get down to this level. And about 2015, we stopped getting better. And that's not because the instruments aren't getting better, that's because the stars themselves create a signature at about 1 meter per second because of all of the changes in their surface, and the planetary signals like Earth are smaller than that. So they just get lost in the noise. So astronomers creatively call this the 1 meter per second barrier, and this is the problem we now need to solve. And now you might be like, Jonathan, I don't believe you. You're all terrible at building instruments. It's really a technology problem. Well, if we go back to looking at the Sun, multiple cutting-edge instruments can make measurements of the Sun and try to measure those radial velocity signatures, how those lines change. And if you look at these plots, all the shape of the lines look the same, which means all of the instruments are saying the star is changing in the same way. And the only way they can do that is if they're measuring it very, very carefully, and it's really the stars that are changing. So we now have to get to the point where we need to figure out and measure what the stars are doing to get to the exoplanets. Question is, so how do we solve that? Well, the answer is through what's called adaptive optics. How many of you have heard of adaptive optics before? Okay, some of you have. How many of you have looked through a heat haze on a summer's day? Think nice warm weather that we have outside right now? None of it. But the heat haze on above a road on a summer's day, that distortion and twinkling of that image. Starlight passes through a distorting, twinkling image called the atmosphere. It's constantly moving and changing. And that twinkling, that is what we see with the stars. It's caused by the light passing through the distorted atmosphere. But what happens if we could correct that effect on the ground? By measuring the starlight 1,000 times a second, reflecting the light off a mirror, like you can see here, which changes its shape 1,000 times a second to correct for those effects and get us back to sharp images as if the atmosphere wasn't there. This is an image from the Large Binocular Telescope of one of these called deformable mirrors that changes its shape to allow us to correct those images. This is what happens behind it. How many of you have sound systems and speakers at home? Okay? The voice coils up here are the same technology that you drive that surface and shape, except here we have magnets stuck on a very thin piece of glass that we can change the shape of 1,000 times a second. And back in 2010, this adaptive optics technology really matured to become common use at telescope facilities, such as the Large Binocular Telescope. So with that, you go, we have this new technology. Does it allow us to get to building new instruments that can help us detect these small exoplanets? And that is the premise of iLocater. So we use adaptive optics in this new technology to get to these low mass exoplanets. Now this was the idea of Professor Justin Crass at the University of Notre Dame, and it was 2012, 2013. I started at Notre Dame in 2014, where we had this concept of an idea, but the question was, how do you implement that? iLocater itself has matured from then to have 4 specific parts, and I'm going to tell you the story of each of them. We have an acquisition camera that takes light from that adaptive optic system and puts it into small fibers. Small optical fibers, I mean 6 microns, which is the 1/10 of a width of a human hair. So we take light from the Large Binocular Telescope that's 8 meters wide. We correct it 1,000 times a second to get rid of the distortions of the atmosphere, and we cram it into a 6-micron fiber. And when I started the project, we had no idea if we could even do that. So that's where we were starting back in 2014. We take the light from those fibers, we put it into a spectrograph to get those spectra to look for those lines, for those signatures of exoplanets. We put it inside a vacuum chamber because this is a very precise measurement, and we cool the instrument down. And then we calibrate the instrument using a wavelength calibration system to make sure we know where the colors of light are going. So 2014 is where we started. We're going to skip forward to 2016. This was my office at Notre Dame. There's going to be a lot of pictures moving forward about the project. And we basically designed a system to take to the Large Binocular Telescope to see if we could get light into those small fibers. This is me, looking a lot younger then, packing the system that we'd built together with the team at Notre Dame, ready to ship it out to the telescope. The person who was really responsible for this was Andrew Bechter, a graduate student at Notre Dame at the time. He now works at Northrop Grumman out in California. And his PhD thesis was working out how to get light in these fibers and get as much light in as we can, because we need light to be able to make these measurements. Another person who was involved with this was someone who was an undergraduate at Notre Dame and just graduated, Ryan Ketterer. He was one of the technicians who worked on this. And this is us reassembling this system at the Large Binocular Telescope, trying to put it on sky. We built the system. This is Justin Krepp, who had the idea. This is Robert Reynolds from the Large Binocular Telescope. Try to figure these two brothers apart. One is Andrew, this is him, this is Eric. Two identical twins on the project. That was a terrifying first day for me, making sure I got them right. So we built the system, went to install it on the telescope. How you do that is you have to crane it. I feel there's a good caption competition moment that needs to go on this picture of what we're looking at. But we then strap it on the side of the telescope. And I look really relaxed. I was told to smile in this picture. What it doesn't show is that this is the edge of the 8.4 meter of the Large Binocular Telescope. And I had to walk around this rim to get here to install it. No one else would do it, so I drew the short straw in that one. So we installed the system, and then we operate it on sky at the Large Binocular Telescope. Simple terms, it worked. Did it work perfectly? Absolutely not. But what it did tell us was what would limit us in getting light in those optical fibers. So we learned a lot in the process of how to get light into those optical fibers at the Large Binocular Telescope. So let's skip forward now from 2016 to 2018 and 2019. We learned those lessons. Came back to Notre Dame. And we went, right, let's go do this properly. Let's not do the duct tape and sticking stuff together with chewing gum. Let's actually go build the instrument that can really do the science. And again, we have a lot of optical components, electrical components, mechanical components there. We build this into this blue box. You can see Andrew here again, testing the system. We use high-powered lasers for some of this, so we have to have laser safety goggles. We build it, we test it at Notre Dame. We pack it up in a box with all of the other stuff that has to go with it, the computers, the electronics, everything together. And we ship it off to the Large Binocular Telescope. And what do we do then? Well, we build it back up together. We have to ship it down there, build it together. And you can see that we have the system here with, actually this is a small simulator of the telescope. It costs about $80,000 to $90,000 a night to operate the Large Binocular Telescope. So you need to make sure that the instrument's really going to work before you put it there. So there's a lot of testing and integration. We finish that integration. Then what you do is you have to crane it up onto the telescope. And we were working on level 1 of the telescope. Where we installed it was level 7. And so they picked it up on a crane on level 1 and craned it all the way up through the building. This is going to get worse, because this is the lower part of the building, And then there's the upper part of the building that this crane continues to go through. I was terrified. They just left it hanging there while they took the elevator from the lower part of the building to the upper part of the building. Here we go. So this is going to come all the way through here now. And then eventually it ends up on the back of the telescope and gets installed into the instrument bay to do science. We put it on sky, we get light in the fiber, and that's our system, that front-end system ready to go for the rest of the instrument. So that was 2019, we installed it. 2020, we were going to go and do a huge amount of testing down at the telescope, a huge amount of characterization. The world had other plans for us at that point, where we ended up being stuck in South Bend for a while. So what we did is we pivoted to the other parts of the instrument that need to be built. That cryostat system, that vacuum chamber, and the spectrograph itself. 2020, in the summer, we were allowed back in the labs at Notre Dame. This is me, dressed up. I was the only person allowed in the lab at the time. It was one person at a time in the lab to do the work. We still had to wear masks, even though there was only one person at a time. And then we had a delivery coming from a vendor who was making the cryostat system. Here it is, delivered to Notre Dame in 2020. And it's sad, because we couldn't really do anything with it until the following year. What we also did, though, is work on the spectrograph components. Again, working with an external company with expertise to build this. They can build systems that are stable with very precise optics. But what they couldn't do is cool the components they were making and checking that the optics wouldn't fall out because the glue would break when it gets cold. So this is what you're seeing here is us testing components at Notre Dame that they provided to us, cooling them down, opening up the chamber and going, is the optic still attached? Before they build the real system. So there's a lot of prototyping and testing we did along the way as well. So, 2021. The world opens up again. We're allowed back in the lab. And we took the lid off that vacuum chamber. And these are two of undergraduates who were at Notre Dame at the time, Matt and Alexa. And that summer, we dug into the cryostat system, the vacuum chamber here, to build space blankets effectively and install them into it. How many of you have seen space blankets? These thin, like aluminum material that you wrap around yourself at the end of a race to keep warm. Okay. So the inside of our cryostat is 85 Kelvin, which is minus 193 Celsius and minus 315 degrees Fahrenheit. That means we need to not allow the warm walls of the vacuum chamber to shine heat, infrared light, onto the insides. And the way we do that is in a clean room at Notre Dame, where we make multi-layer insulation, as it's called. This is the same stuff you see on spacecraft from NASA, and effectively, it is putting sheets of aluminized mylar, just aluminum foil effectively, with spacing material between, nylon twill. It's the same material you make ballet dresses from. We actually buy it from a company that does that because it's a lot cheaper than getting the space grade stuff. And you basically put out templates, you lay these down in the clean room at Notre Dame, build them up, and then eventually you fit them into the vacuum chamber. You then have all of the internal components that support the rest of the instrument. The internals are all fabricated at Notre Dame in the physics machine shop. And you put it together. Now, what also happened in 2022 is I decided I was moving to Ohio State. What that means is the instrument also has to move to Ohio State to be finished, because that's where I am and the other team who can work on it. So, beginning of 2023, we come back to Notre Dame. We fit things onto the instrument cart to make it really ready for shipping. We then load it onto its own customized pallet. This cryostat system, I've never before designed a pallet for a specific scientific instrument, but we did. We had John, who's the machinist from Notre Dame, and Mike, who's one of the mechanical engineers from Ohio State, both come to help with this process. We have the nice pictures of them, and then we have the pictures of really building an instrument where you're hiding underneath to do the things that need to get done and inflating things. We'd spent a lot of time and effort designing this shipping crate. It moved across campus at Notre Dame on the back of this truck. The most terrifying thing for me at this part was not getting onto the truck. It's when I got it off the truck and I realized how much the bottom of this crate was actually flexing as we lifted it. Again, now about that, we've gone and reinforced it. It's fine. At the time, I thought it was all going to fall apart. It was all going to come off crashing down. But we pack it up. We ship it across to Columbus, the cryostats inside here. This is all of the other equipment that has to come with it. The left-hand side image here is when the truck left from central receiving at Notre Dame. You can see it's nicely tucked up against this strap at the back. This is what happened when we opened it at Columbus. Apparently, there'd been a few bumps along the way and the whole cart had moved. The lesson is you strap at both sides of this. And when we ship it to Arizona, that's exactly what we'll do. There was no harm, but it came off the truck in Columbus. We unpacked it, inspected it. We actually had loggers in here, so we know that nothing really bad had happened. Even it had gently slid forward in the truck, nothing too severe. And we installed it in the lab, in the clean room in Columbus. So that's the cryostat. But that's only part of the problem. What about the spectrograph? 2 weeks later, we had another delivery to Columbus. And in this wooden box is actually the spectrograph coming from the vendor. These two met for the first time later that year. And we started a series of more testing to understand how the instrument's going to perform. So that was 2023. 2024. This was the year of electronics, is the way I describe it, because we had a vacuum system, a cryostat system, but we had no way to know what was happening inside of it because we had no electrical in there, no sensors, no ability to control the system. So we built out all of the electrics inside here. Instruments are complicated. They need a lot of sensors, a lot of electronics, and this is the electronics rack for iLocater. We added sensors everywhere. The detector in the system, we actually have sensors. There's heaters and sensors in here. For cost, these sensors can measure to better than 100,000th of a degree, but they also cost $1,000 each. So because we're trying to do precision science, we need them, but it can be pretty expensive. So we continue to integrate. No instrument is complete without a nice shiny logo and the institution logos on, so they were added that year as well. And at this point, we could actually go back to the Large Binocular Telescope and we could complete the testing that we hadn't been able to do in 2020. So we took this thing here. This is what we call LILY, which is short for Little iLocater, hence LILY, Little iLocater. And this was a collaboration with Durham University in the UK. They provided this, and it allowed us to look at the light we were getting into those fibers. This is the first ever spectrum we got from iLocater. It's why we all look really happy, even though this is stupidly early in the morning. Now, it's a big telescope. It's 8.4 meters across. So you would think we'd look at like a faint star or something else. How many of you have heard the star Vega? It's the 5th brightest star in the sky. Well, that's what we looked at, because it's easy. But it demonstrated that we can actually get the light in the fibers, and we're really ready to start doing science with the LBT. So that was 2024. What about this year? Well, I got a very late Christmas present this year where we actually got the detector and the electronics for the detector delivered to the project from NASA Goddard. And the detector that iLocater is using is one from the Nancy Grace Roman Space Telescope. It's NASA's new flagship mission. It's launching next year. We'll come back to that in a little bit. But it's got a lot of special properties and improvements in performance that's going to allow us to do better science. So NASA has loaned us this detector and delivered it to us in January. They also delivered the fibers that take light into the vacuum chamber. This is Rob from the photonics group at NASA Goddard installing those with Mike again, this time dressed up nicely in the clean room rather than installing everything on the outside of the vacuum chamber. So we installed that, put it together. And since then, we've been doing testing on the whole system. Now, I said that we need to hold this instrument very cold, and it has to be stable. So when you think stable, you might think, 1 degree, or half a degree, or a tenth of a degree, or a hundredth of a degree, or a thousandth of a degree. We are holding the instrument stable to better than 1/10,000th of a degree, because that's what the science needs, and that's why we need those really expensive sensors. So this is actually data from July this year, where we stabilized the instrument and demonstrated its performance. Lots of data points, but we're seeing this at a fraction of a millikelvin. We also have gratings that got delivered to the project. This is me looking nice and colorful in my nice outfit in the clean room. We installed that into the instrument in August. So if we come back to this image of the sun, this is a visible light spectrum of the sun from Kitt Peak. This is the iLocater equivalent taken out of the lab window at Ohio State. This is a real solar spectrum taken with iLocater from earlier this year. So everyone got really excited about it. If you're interested, you can scan the QR code. There'll be a link at the end. You can go look at some of these things. And this is the state of the instrument as of Wednesday last week. We've buttoned it up again and we're cooling it down for the 13th cool down this time. But we're really starting to come together with a complete instrument. And we actually passed our pre-ship review in the middle of October, allowing us to go to the telescope as soon as the telescope's ready to receive us, which is incredibly exciting for the project. So, what's going to happen if I get my crystal ball out and tell you 2026 into the future? Well, iLocater is expected to ship to the Large Binocular Telescope in the spring next year. Hopefully in March is what we're aiming for. And we'll then go through a whole process of checking the instrument survived shipping, making sure that we get the same performance we demonstrated in the lab at Ohio State. When we've done that, we'll start taking observations of the sun to try to add additional data points on those plots that you saw before of how other instruments are looking at the sun. And we'll start doing real science, using the LBT and its adaptive optic systems to study the night sky and start studying those exoplanets. One of the things that we're going to be looking at is something that many people will say it's very science fiction. 1977, before I was born, Star Wars movie came out, and it had this circumbinary planet, Tatooine. You can see the image of it here. We think about half the stars in the universe, in our galaxy, come in pairs, these binary star systems. The problem is, normal spectrographs, because they don't use adaptive optics, just have this distorted smudge of this light mixing together. And iLocater is going to start being able to separate these out for the first time and study them in a way we've never been able to do before. So the rest of the exoplanet science is great, but saying we're able to study Tatooine is kind of pretty cool as well. So iLocater is going to be doing a lot of science, but I want to say that it's 10 years in the making. Is that unusual? Next year, we're also going to get a new flagship mission launching from NASA. And this is named after the lady you can see here on the left-hand side. This is Nancy Grace Roman. She was born in 1925, did an undergraduate degree and a doctorate in astronomy from the University of Chicago in 1949. She loved teaching, she loved research, and had a whole suite of experience. But in the 1940s and 1950s, science was not as open to everybody as it is now. Come 1959, however, an employee at the new NASA approached her about people who might be interested in creating a space-based astronomy program. And by 1960, Nancy Grace Roman was herself serving as NASA's Chief of Astronomy and Relativity. And she devoted 20 years advocating for and pushing for what was known at the time as the Large Space Telescope and became to be known as the Hubble Space Telescope. So she's often known as the mother of the Hubble Space Telescope. That's what you can see in the image here. In 2017, she achieved pop culture fame with her inclusion in the Women of NASA Lego set. And unfortunately in 2018, we actually lost her. She passed away. But in May of 2020, 15 months after her passing, NASA announced their next flagship mission, which is what you can see here, was going to be named in her honor. So the Nancy Grace Roman Space Telescope is designed to explore questions regarding dark energy, exoplanets, and infrared astrophysics. This fall, the whole telescope system passed a series of key tests. It has to be shake tested, acoustically tested, and thermally tested to make sure it's going to survive launch and work in space. And that actually happened successfully during the government shutdown. So it's a testimony to the people who continued to work on that over a 65-day period for that thermal testing process. The launch of the Nancy Grace Roman Space Telescope is actually expected in September 2026. That is actually earlier than they previously predicted. They're ahead of schedule. So launching in 2026, when was this idea conceived? Every 10 years, the US astronomical community comes together and puts together a decadal report and says, what are the highest priority things for astronomy we should be doing for the next decade? And this mission was the highest ranked thing in the 2010 decadal survey. It was efficiently adopted in 2016 by NASA, and it's launching 10 years later. So these projects are complicated. You're doing something you've never maybe done before, and you're pushing the boundaries of technology, and it takes time to be able to do that. So iLocater taking a while is not unusual when we're trying to push the boundaries of technology. So why is Roman important for exoplanets? Well, I said we know of 6,000 exoplanets today. Roman is expected to detect 100,000 transiting exoplanets over its mission. And it's also expected to discover 2,500 planets by the technique of microlensing. What's different about microlensing from the transit technique is it helps probe smaller planets and planets further out from their star that we're not able to detect with the technologies today. So aside from it doing fantastic science generally, it's going to change how we understand how our solar system fits into those broader exoplanets as well. So again, I'm excited about iLocater coming online next year, but I'm also really excited about Roman. And it's really cool that we get to use one of their detectors in our instrument as well. If you want to know more about iLocater, we have our website address down there, but I'm going to pause here and stop and take questions.
Where is the Large Binocular Telescope located?
Great question. So where's the Large Binocular Telescope located? It's down in Mount Graham, down in Arizona. Arizona. So it's about 2 hours east of Tucson. Go ahead.
I'm trying to wrap my head around the reason why you need the micron fibers.
Mm-hmm. So, great question. So why do we need those small fibers? Do you have a fiber? Have you seen a fiber optic Christmas tree before? So we have those fibers, right? They're pretty big. They're pretty robust. If you ever look at the output of them and shine them on a screen and you move the fiber around, that output will change. It's actually what we call a multi-mode fiber, and you get changing illumination coming out those fibers. Modal noise is what we call this in astronomy. And we're trying to make an incredibly precise measurement, and when your fibers change illumination, when you're making that measurement, it's really, really hard to make that measurement. That's if you have fibers that are maybe 100 microns or bigger. The smaller and smaller you make that fiber, the less that pattern can change. And as you get to the very, very small fibers at 6 microns, for us, it changes a little bit with the color of light. You end up where there's only one pattern you get out out of those fibers. So instead of having a multi-mode fiber, it's called a single mode fiber. And that's the specific thing that's enabling iLocater to do its science. When I move a single mode fiber around, the output stays the same. It doesn't change. So if we're trying to make a really stable measurement, having a nice stable output is what we need. But we need adaptive optics to be able to get the light in those fibers in the first place. The big fibers, don't need it. That's what the seeing limited existing spectrographs use. But with adaptive optics, we can go to those really small fibers to get the light in them. And that means it's a nice stable pattern to illuminate the spectrograph to do these really precise measurements we want to do. It's a really good question.
The graph on the exoplanets is looking at the atmospheres of the exoplanets.
So the question is sort of what science can we do with the spectrograph? So we can look at the colors of the lines and how they shift to get that Doppler signature to see the planets exist. We can do what's called transit spectroscopy. So if we have that cartoon of the transit, again, where the planet passes in front of the star, it blocks out some of the light. So we can actually take a spectrum, look at the colors of the light of the star when the planet is not there, do it again when the planet's in front, and we can compare the two. And by comparing the two, we can look at the chemical composition of the planet's atmosphere. This is what we call transit spectroscopy. And yes, we're going to be able to do that with iLocater. A lot of people are very excited about helium. Helium, obviously, is like helium balloons. It likes to escape out of atmospheres. So it's a really interesting element for studying sort of planet formation, how planets change. And so we can do that with iLocater with the high resolution, and that's what we're going to be able to do.
You'll also be able to detect methane and CO2.
There's all kinds of things we'll be able to detect. We'll see water. The problem with doing water from the ground is we also have water on Earth, so it's sometimes hard to disentangle it. So that's why for water particularly you're better in space with the James Webb Space Telescope, for example. But there's all kinds of things we can look at with those different lines in the spectra. They'll tell us about different chemical elements or molecules that we can see, and that's how we know what the planets are made up of in the atmospheres.
So will it help answer the question, are we alone?
Will iLocater answer the question of are we alone? Probably not. It will help detect a lot of planets and give better constraints on masses of planets. But just because a planet is there doesn't mean it can support life. So let's say, for example, we look at Mars, right? We think Mars had liquid water at one point. We have not seen evidence that there is life on Mars at this point in time. So just because we know a planet has mass and it's just about the right place, potentially, it could tell us that it exists. It doesn't tell us about the signatures of life. And this is actually a really active research topic at the moment for a future mission that came out of the 2020 decadal survey called the Habitable Worlds Observatory, which is designed to basically try to characterize nearby Earth-like planets around sun-like stars in our galaxy, to try to answer the question of, is there life there? The problem right now is we don't actually know what to look for. Because if you're looking at carbon dioxide or carbon monoxide, there are biological processes that can create that. There's also physical processes and geology that can cause that. One needs life, one doesn't. The Earth has had different cycles and periods where you get different signatures. And so we're still trying to figure out of what are the things we need to look for if we want to try and detect these planets properly and see if there's life out there. Habitable worlds will go a way to say something, but will it definitively be able to say something right now? We don't know. We still are trying to answer that question to know what that new telescope that would probably launch in 2040 something might be able to answer. It's a very active area of research. It's a good question. Other questions? Yep.
That adaptive mirror that takes out the distortion in the atmosphere, is that on the Large Binocular Telescope, or is that part of your equipment?
Good question. So the question is, for the adaptive mirror, that deformable mirror that corrects the atmosphere, where is that? So actually that is part of the telescope. The telescope has its big 8.4 meter primary mirror, and that deformable mirror is the next mirror in the system. It is 90 centimeters across. It has, I think, 672 actuators behind it, those little magnets. And it is, I think, 0.9 millimeters thin. It's a thin shell that you just stored. But it's there for scientific reasons. It helps provide correction to lots of instruments. It also means that for infrared instruments particularly, you want to minimize the number of surfaces you hit so you can do really good science. So that's why they put it up there. It's a lot of science that's really driving putting it there. The engineers would prefer it in a nice contained box and not out in the open, but science says we have to have it up there for doing it.
What's that mirror made out of?
What is the mirror made out of? I can't remember exactly which type of glass it is, but it's just a very thin piece of glass that's distorted. Yeah, yep, exactly. So, is there a question?
The Nancy Grace, is that the one that was made out of the spy satellite that was given to NASA?
Yes is the quick answer. So the history of the Nancy Grace Roman Space Telescope, I am not an expert on this, but yes. There was another 2.4 meter mirror that a federal agency went to NASA and went, hey, we have this spare mirror, would you like it? NASA went, yes please, and that's the premise of what the core of that telescope is. Yes, go ahead.
Will you be able to use iLocater to follow up intrasolar system transits like Webb's recent capture of Uranus' transit with the star?
Good question. So the question was, I've been talking a lot about iLocater and exoplanets, but can it do things in our solar system? Yes. We've actually been talking internally among the team about what is the first thing we should look at with iLocater. And they're like, well, we could do this star. Astronomers don't necessarily come up with the best names of interesting stars to look at. So you could be like, the first star we're going to look at is HD number. Is not as cool as like, hey, we looked at one of the moons of Jupiter. So we can do things. How it works with telescope time is you have to have a really good science program. So if it costs $80,000 a night to run the telescope, you want to make sure that you're doing good science with that rather than just sort of wasting the time and wasting the money. So there are highly likely a lot of solar system programs that would benefit from iLocater. We could potentially scan a fiber across and do spectral mapping or something, depending on the science case. But there's nothing stopping us doing that, providing we can use the adaptive optics system to get the light in those fibers in the first place. So, good question. Is there another question at the back?
Follow-up actually on I forget the diameter of the fiber.
Yep.
Sorry, I came late. You were speaking of the luminosity, I think, in the variance. Does that also have spectral distortion as well, and that's reduced?
That's a good question. So the question is, with the single mode fibers that we're using for iLocater, you don't have the spatial distortions, the changing images coming out of it. Does that change with wavelength as well? A little bit. It's complicated. We've done a little bit of characterization of that previously, and it looks to be okay. We can correct it in the data reduction pipeline. A lot of astronomers will it's like, we'll fix it in post. We do as much as we can in the instrument, but sometimes you just have to take these things out in the data reduction process. And how we are going to handle the data from the instrument to go from a detector frame to radial velocities, we're going to have to figure out. It's a research project because our instrument is so different from existing ones. So we can use a lot of their heritage, but then we still have to build on top of it to make it work for iLocater. So we have a team at Ohio State, and Marshall Johnson, who's a research scientist there, and Marcelo Talla, who's a postdoc there, that's going to be their job once we get iLocater on Sky next year, is really trying to figure out how to use the instrument to make the best science out of it. It does. One question back, yeah.
Tell the story of how Nancy Grace Roman suspected dark matter.
I honestly actually don't know a lot about Nancy Grace Roman's history. I know a little bit, and I've been looking more at the telescope and stuff. She is a fantastic character. If you go back and look at some of the stories, one of the comments she made was about the Hubble Space Telescope. She was like, even without me, it would have probably been made at some point. But I'm much happier it was made while I was around. And just her perspective on engaging the public with science and teaching has been more what I've focused on. I think she's been a real advocate for, broadening engagement with science, but also advocating and pushing for the technology. One of the big things she did with Hubble was push for CCDs to be used. And they're now ubiquitous. And it was her saying, no, we need to be better than, an initial idea for Hubble was dropping glass photographic plates from a space telescope on a parachute to bring them down because we didn't have the technology. And she was like, no, just no, let's do something better with CCD. So I know more about the technological side, not necessarily the science side. But I'm sure we're going to hear a lot more next year about her legacy, both on the technology side and the science she's wanted to do as well. So, yes?
Speaking of telescope time, I'm aware of the NASA Citizen Science Project
Mm-hmm.
involved detecting exoplanet transits, follow-up to TESS.
Mm-hmm.
Another exoplanet survey.
Yeah, so
Do you have any thoughts about the value of citizen science projects like that?
that's a really good question. So I talked a little bit about the Kepler mission, which was sort of the first transiting exoplanet mission. That's now been superseded by TESS, which is still going strong. Kepler's been retired. And citizen science was actually really important because astronomers don't have time to look at everything. And humans are really good at spotting things that are weird. AI is a big topic at the moment, as is machine learning, as it's been called in science previously, before it kind of came into the public for. And I would say I'm usually the person in the audience when we have a talk about using machine learning in science, where I ask the question of, well, how did you train your data? And we've seen this with the stories we see about AI of how did you train your thing to make sure it's giving you real answers to something. And you have to have a good data set to train it on. And a good way to do that is human eye. We're really good at recognizing patterns and spotting things that are weird. So there is an important component there for citizen science still. I think it's also just a great way to engage people with what we're doing in research, making them interested in contributing to something that's an active area of understanding how the universe works. So I think it's really important. I think we should do more of it. There's all kinds of stuff, whether you're interested in planets or galaxies, all kind of citizen science that's out there. It's really kind of important. So, do you have a question, Dave?
Yeah, about calibrating the adaptive optics. What tool is used to tell the maggots which one moves how much and when?
That's a good question. So how does adaptive optics work and how do we know what to do with the mirror? You effectively go and poke every one of those things, every one of those actuators, and see how it responds. That's literally it. They have a wavefront sensor that measures it. We know what stars should look like. They push each of the elements on the mirror, see what happens and measure it.
It just keeps getting clearer and clearer and clearer, and then...
Not exactly. So you do this beforehand to know how the system responds. And then after the fact, when you've built what we call an interaction matrix, is the technical term for it, you can then use that in real time to say, I know a star should look like a point. I'm measuring a splodge, but I can measure that splodge, and so I can figure out what happened between. And then it's like taking a distorted piece of metal and hammering it back into the shape in real time with the mirror. So you basically do a lot of calibrations to know how the mirror responds, and then the computers in real time can figure it out. It's a lot of mathematics.
Changing doesn't really affect it once it's calibrated.
The atmosphere is always changing, but the system knows how to correct that effect. When you give it a distortion, it knows how to correct it. It's going through a big calibration process. So I'm conscious of time. So do you want to wrap up and ask anyone else has one final question? Why the Large Binocular Telescope? Because Notre Dame's a partner in it. So we have, Notre Dame is a partner in the Large Binocular Telescope, so we have access to it. Ohio State also is a partner in the Large Binocular Telescope, which is why it's more convenient and easy for me to go to Ohio State and still work on the project to kind of get it finished. So
It wasn't a special science requirement, right?
it was not a special science requirement. There are other facilities that can do it, but obviously if you have access to something, you want to use it and do the best science you can with it. And iLocater, in my opinion, is one of the best things we can do with it. So that's why we're building it for there. So awesome. We'll wrap up there. Did you have an extra couple of things?
Indeed. Well, so first let's thank Jonathan. And let's see. Oh no, sorry. So I just want to thank you all for being here. We will start up again in February. So if you watch the Our Universe Revealed website as we get events up, we'll be sending them out through the listserv. They'll also come up on the website, and they'll also be published through the library. So anyway, that's it for tonight. And if you have additional questions for Jonathan, I'm sure he'd be happy to answer them. And thanks.
Thanks you all for coming.